Hey. All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. It looks like my camera's not working right now, but I'm still here. Does everyone in Zoom, can you guys hear me? Hear me okay?
Yes.
Okay, good. Okay, so you can hear me, but you can't see me today. But I guess we'll be okay with that. All right, so how's everyone doing today? Happy Valentine's Day, by the way. Good, good. All right. Okay, so our plan for today is we're going to continue on with our lecture notes on fins. So we have quite a bit of ground to cover this week because I do want to finish up all the 2D stuff and by the end of this week. Just because next Monday is a holiday, and so next Monday we're not going to have class. But I will still have office hours on Monday. It'll just be virtual. It'll just be from my home, but we're not going to have class next Monday. So, I want to make sure we kind of get caught up this week. To kind of next Monday. Yeah. Next Monday is President's Day. Yeah. So we have homework due on a holiday. We have homework due on a holiday. Yes. Yeah. Yeah. So I do plan on still having office hours on Monday. It'll just be purely virtual. And so if you have any last questions on the homework, you can pop into to Zoom and then ask them. Wait a second. Well, I mean, I'll be closing the office hours at noon. And so. Oh yes, yeah. Yeah, because office hours are Monday, 11 a.m. to noon, and so yeah. So I'll be on Zoom during that time, so you can come in and ask questions. Okay. All right. And so I think that's all my announcements. And so, are there any questions before we get started today? Okay. All right. So let's go ahead and get started. And so where we left off on last Wednesdays, we were talking about heat transfer from fins. Okay. And a fin is a fairly common structure that you would make in thermal engineering. And the whole idea with the fin is to increase the surface area whatever object that you have, okay? Okay. And the whole idea of, and the reason you would want to increase the surface area of an object is to enhance the convection heat transfer that comes off of it, okay? And so for most cases, fins are put in place to enhance convection cooling. And so if you have a very hot part, like a computer part, if you have something like an engine where you need to offload heat very quickly, so just to make sure that you don't melt whatever device that you're designing, you put a fin on there so that you can offload heat at a much faster rate. Because if you compare two cases, and so if you kind of make a zoomed in shot at an object, right? And so this would be like the wall of your object. And so the object would be on this side. Okay. And let's just say for the sake of simplicity, you have air cooling on the outside. Okay. Right. And so if you, if you don't have a fin, of course, there's going to be heat that leaves this object like this, right? We'll call that Q loss. Right? If you compare that situation to one where you do have a fin, or in this case, I'll put several fins, okay? And just like before, we'll have air cooling. Okay, here's the object. Right? If you compare the situation on the right, you're going to have much more convective cooling. It's because you just have more surface area, right? And so you have more places where the air can contact the object, and thus more places for you to offload more heat. Okay. So fins are a very fundamental and very essential part of thermal engineering, because they let you, enhance the amount of heat transfer, heat loss from your system, a lot of times without really changing the shape or really doing too much to the design. It's just kind of like an exterior feature that you can add on top. Okay? And I think where we left off was we were talking about the fin heat equations. Okay? Right, and so our heat equation looks something like this. And so we have d squared T dx squared plus 1 over AC. Remember, AC is the cross-sectional area of the fin. Okay. And so that was the equation that we were starting with, where we made the assumption that we can cross out this term. Okay. And the reason we could cancel this term was we were assuming that the cross-sectional area was constant. Okay. And if we have a constant cross-sectional area, that means its rate of change, or dAc dx, is going to be equal to 0. Okay. And hence that whole term is going to be equal to 0. Okay. Okay. And so the other relationship that we're going to assume that we didn't have time to go over last time was regarding this term right here. Okay. Remember, AS is the surface area of the outside of the at the outside of the fin. Okay. Okay. And thus dAs dx is the rate at which the surface area is increasing as you go along the fin, okay? But we can come up with a very simplified expression for this, based on the fact that we are assuming that the cross-sectional area is constant, okay? So let me draw you a picture just to kind of show you how we derive that term. All right, so here we have a typical fin, okay? Let's say the fin is cylindrical, oops. Right, so let's assume the fin is cylindrical, and so this, a certain cross-section has a perimeter P. And let's say that this perimeter is measured at some distance x away from the base, okay? All right, and so if we take these two parameters here, we can take their product in order to get the surface area of the fin up to that location x, okay? Okay, and so we have AS of x is equal to, in this case, it's just going to be the product. And so we have the perimeter multiplied by the distance x, okay? Right. Any questions on how we got that relationship there? About how, we take the perimeter, we just multiply by the distance x, and that gives us the outer surface area of the fin. And this is valid whether we have a cylindrical cross-section or not, or a circular cross-section or not. I just drew a circular one just because I think it's a little bit easier to visualize. But if you have like a rectangular fin, or if you have an ellipsoidal fin, or any fin, this relationship will hold. Okay. All right, and so if we have this expression here for AS, if we take the derivative of this, right, we have this x right here, and so that x is going to go away. And so all we're left with is the perimeter P, okay? And so let's use this perimeter P in our fin equation up here. And so we can finally get our last simplification. So we can get the final relationship that we ended up with last time, okay? All right, and so if we plug that in, then our fin equation is reduced to our first second order derivative is still going to be the same. Okay, so that doesn't change. Then we have h times p divided by KAC multiplied by t minus t infinity is equal to 0. Okay. Where we have kind of two kind of distinct terms here, and they kind of represent two different things, right? And so this second order derivative, this d squared t dx squared, this makes us think of our heat equation for conduction, right? So the heat equation that we've basically been working with for the last 2 weeks, okay? Okay, and that's going to be the heat transfer due to conduction down the length of the fin itself, okay? Whereas this term right here, this has a relationship that looks like our convection, Newton's law of cooling, right? And so this is our heat loss due to convection. Mostly because there's an H here, and whenever you have an H, then that means there's convection. And we have this kind of T minus T infinity, which is the same as convection, okay? And so our heat equation is for fins is kind of a relationship between these two, okay? If you want a visual indication or visual representation of this, we have our fin like this, okay? Usually what's going to happen is that the base of the fin is going to be hotter than the ambient temperature. And so we have T base. Okay. Right. So that's the temperature of the base of the fin. And of course, we have T infinity. Okay. And so usually, for most cases, T base is going to be greater than T infinity. Okay. And so you're going to have heat transfer that goes from the base out to the edges of the fin. Right. And so on the one hand, you have heat that's going down the length of the fin like this. Okay. And since it's traveling along the solid part of the fin, that's heat transfer due to conduction. Okay. And so that's represented by the second order derivative term up there. And at the same time, in a direction that's perpendicular to that conduction, we have the heat loss of the fluid due to convection. Okay, so we have heat coming out. This is Q convection. Okay. And remember, the most defining trait of the heat transfer that we're considering this week is the fact that Q conduction and Q convection are going in different directions. Okay. Right, so that's a visual kind of representation of what the equation is expressing. All right. Any questions on this? Okay. All right. And so technically, we can solve this equation, right? And so if we look at this equation right here, it's basically a second order differential equation. It's not as simple as the ones we were working with before, because before we were saying that basically d squared t dx squared is equal to 0. But now we have this t right here, right? And so now t is actually part of the equation. So that makes it a little bit more difficult to solve, but we can still solve it, right? As you think back to what you learned in Math 250A, what you learned in EGME 308, then this is kind of child's play, although it's still a little bit tedious, okay? But we can make it even easier for us. And so this is not maybe you'll disagree with me, but this is not a math class, and so we focus most on the heat transfer here. And so when we can simplify the math as much as we can, then we're going to do that. Okay. And so instead of solving this equation right here, which is a second order differential equation, but it is an inhomogeneous differential equation because we have the T infinity, let's try to make this a little bit easier. Let's try to make it a homogeneous equation. And so let's perform a change of variables. Okay. I'm going to define a new variable, which we'll call theta. Okay. And this theta right here, I'm going to define it to be what's called the excess temperature. Okay. So it has the exact same units of temperature. It just has a different representation. Okay. And so this excess temperature is going to be defined as the temperature of our fin, T of x, minus the fluid temperature. Okay. And so it's just going to be basically T minus T infinity. Right? So where this gets this name, or the reason we call it excess temperature is, it's literally the temperature in excess of the fluid, right? And so we take whatever temperature the fin is, we subtract the fluid temperature, and that's how much excess that we have. And that's why we call it that. Okay. All right. So how does this help us? And so let's do another thing. So let's take excess temperature, and let's take the second derivative of it. Okay, so let's take d squared theta dx squared. Okay. And so we're going to take a derivative of this expression twice. Okay. Since T of x here is a constant, when we take the derivative of it, it's just going to go away. And so all we're left with is d squared t dx squared. Okay. Yep. T infinity is a constant, yes. Yeah, so when we take the derivative of theta, then the T infinity is just going to go away. Yeah. Mm-hmm. All right. So now that we've defined these two variables, let's go ahead and plug these back into our heat equation. Okay? And so first of all, we can make this direct substitution where we say that d squared theta dx squared is exactly equal to d squared t dx squared. And so we can take this and just plug it right in for this. Okay? So there's a 1-to-1 correlation there. Okay. Meanwhile, for this theta, this is going to be equal to t minus t infinity. And so we can go ahead and plug that in for this entire expression right here. Okay. And this is great for us because then this is going to eliminate our our inhomogeneity of this equation. Okay. All right. And so once we do that, we're left with the final form of this equation that this is the one that we're gonna end up solving. Okay. And so we end up with d squared theta dx squared minus h over p divided by KAC times theta is equal to 0. Okay. Right, and so we'll call this our fin equation for a constant cross-sectional area. And this is the one that we're ultimately going to end up solving. All right. Any questions on how we obtain this equation here? Okay. All right. And so what we have here is a second order ODE. Okay. And through our change of variables, we basically made this equation homogeneous. Okay. So it's good. So we don't have to do any, man, it's been so long since I thought through away. I forgot the name of it already, but we don't have to do any kind of guess and check, polynomial bullshit, anything like that. So we can just kind of solve this directly from the characteristic equation, okay? Does everyone remember when they took 308 and how they solved these kinds of equations? It's okay, I understand. I remember when I learned when I first went to heat transfer, it was about a year after I took engineering math, and it was kind of well for me too. But whenever you have an equation like this, where you have basically the second order derivative of the variable that you're trying to solve for, and you have the variable itself here, you can form what's called the characteristic equation. Okay. All right. And so the idea with the characteristic equation is that you're going to form a polynomial here to help us solve the differential equation. Okay. And so you're basically going to replace the orders of the derivative with a polynomial term of the same order. Okay. And so the polynomial variable that we usually use is lambda. Okay. And so for this term right here, which is the second order derivative, I'm going to replace it with the second order polynomial, which is lambda squared. Okay. And then you bring down the minus sign, you bring down the constant as well. Okay. And then for the first order term here, which is no derivative, we transfer down nothing. Okay. And so we end up with lambda squared minus HP over KAC is equal to 0. Okay. And from here, we can solve for the roots of lambda. Okay. Which in this case it's fairly simple because we can just move the HP over KAC to the other side and take the square root. Okay. And so if we do that, we get lambda squared is equal to HP divided by KAC. Okay. We take the square root. We get lambda is equal to square root of HP over KAC. Okay. All right. And so, the reason I put plus or minus there is because, when you square something, you take the square root, it can be either positive or negative, right? And so now that we solve for lambda, we can say that lambda 1, we'll call lambda 1 is equal to positive HP over KAC, okay? And lambda 2 is equal to minus square root of HP over KAC, okay? Right? And so once you found the roots of the characteristic equation, then what you say is our general solution here, phi of x is equal to C1 e to the lambda 1 x plus C2 e to the lambda 2 x. Okay. All right. And so if we go ahead and plug in our values for lambda 1, lambda 2, then we get phi of x is equal to C1 e to the square root HP over KAC X plus C2E, the minus HP over KAC X. Okay. And so this here is our general solution. To the Finn equation. And of course, the next step, whenever we see C1, C2, we want to get rid of those constants, right? And so we're going to apply boundary conditions on this equation to solve for C1 and C2. All right. And so a little flashback to your math classes. Any questions on this? Okay. Okay. So now, okay. Now, just like we've always done with the heat equation, it's time to apply our boundary conditions. Okay, and we have a lot of options here, and so there's quite a few conditions that we can apply. Some that are a lot more work than the other ones. Okay? But no matter what, for all cases, we're going to assume that we know the temperature at the base. Okay. Okay. All right, and so the base temperature, we'll define that as TB, okay? And so if we know what TB is, then we know what theta B is, because theta B is just going to be the excess temperature at the base, okay? Okay. And so theta B here is excess temperature at the base. Okay. Okay. We know where the base is, and so the base is at x is equal to 0. Okay. And so we put all these together, what we can say is theta at x is equal to 0 is equal to theta B. Okay. And so this boundary condition is known as the base condition. Okay. And for the sake of this class, we're always going to use this condition. Okay, so this one will always apply. And so practically speaking, I think while everyone's writing that down, this is not a bad assumption, because a lot of times when you're doing thermal design of a certain device, like you're doing thermal design of like a computer part or of an engine, like exactly what temperature that you want to avoid, right? So you know that the metal on your engine is going to melt at a certain temperature. You know that the metal inside your computer is going to melt at a certain temperature, and so that kind of represents your worst case scenario. And so when you're designing your fin, you can set the base temperature or the excess base temperature to be basically what that is. And so you set it to be the worst case. And so if your fin can kind of handle that kind of heat load and can kind of offload that heat in an efficient manner, your fin's going to perform at kind of that worst case. And so most of the time, this is a very reasonable assumption to know. Okay. That's what you're designing around most of the time. All right, any questions on this? Okay. Okay, so that's the base condition. So that's fairly straightforward. The part where we have options is the boundary condition at the other side of the fin, right? And so the other side of the fin, opposite from the base, is going to be the tip. Okay. And so for the tip conditions, we have multiple different options here, depending on what you can assume about the situation. Okay. And so we'll call this tip boundary conditions. Okay. And so there's four options. Okay. We're not going to go through. We're only going to go through one of them in detail, which is the easiest one. But I do have some details about the other tip conditions in the notes if you're curious. Okay. Okay. And so I'm going to go ahead and list out what the four tip conditions are, and then we'll discuss which ones we're going to discuss. Okay. Okay. So the first tip condition is perhaps the most general one. It's also the one that requires the most work. But this tip condition assumes that we have convection heat transfer from the tip. Okay. Okay. And so visually it looks something like this. Okay. And so here is our fin. And so what we've computed so far is the fact that as you travel along the fin, you know, heat is going to leave the fin through convection off the lateral surface. Okay. Okay. But when we say that we also have convection heat transfer from the tip, what we're saying is that off of this tip surface right here, okay, parallel with the conduction heat transfer, we're also going to have convection heat transfer that goes out the same way. Okay. Right. And so intuitively, I think this is the one that makes the most physical sense to everyone, because, you know, we already have convection heat transfer off the lateral surface. And so it only makes sense that we have convection heat transfer out of the tip as well. Okay. But mathematically, this is the most complicated one. And so we're not going to go through the details of this one, but I will show you how to set it up in case you are curious. Okay. And so we set this up just like a convection type condition that we've set up before for our heat equation. And so mathematically it looks something like this. And so we have H times AC times T at L minus T infinity is equal to minus KAC times dt dx at x is equal to L. Okay. If we substitute our excess temperature here, just to make this mathematically a little bit easier, then we have HAC. We substitute theta here, as we have theta of L is equal to minus KAC times d theta dx, evaluated at x is equal to L. Okay. Where L is the length of the fin. So L is this length. And so, you know, visually, you know, this might not seem like it's that bad, because, you know, you're probably saying that we've already done this for, you know, for our regular heat equation. And so, you know, doing this for the fin shouldn't be as bad, right? The difficult thing for our fin solution is that we have these exponentials here. Okay. And so when you plug in x is equal to L here, both in the derivative and from the temperature distribution, you're going to have a lot of exponentials just kind of floating around. And so it's a lot of algebra to kind of keep track of all these exponentials to and from, you know, the different parts of the solution. So, you know, it is intense. So the first time I taught this class, I actually went through that solution of how to apply this condition. And it took over half the class just to go through all the algebra. It took over half the class, and I think 0% of the class got anything of value from that. And so I think I'm not going to do it again, but you know, but I did want to show it to you just because you know, this is the most general case, and you know, it's because it accounts for all different sizes of fins. Because what you'll see for the other tip conditions is that we have to make some assumptions. mostly reasonable assumptions on, on the geometry of the fin. Okay. Okay. Any questions on this? Okay. All right. So that's the first condition, or first tip condition. Okay. Number two. Okay. The second tip condition is that we're going to assume that the heat loss at the tip of the fin is negligible. Okay. Okay. In other words, if we assume that the heat transfer off the tip, just the tip of the fin is small, then we can basically assume that the tip is adiabatic. Okay. Okay. Right. And so remember how we formulated an adiabatic boundary condition, right? And so when we say it's adiabatic, that means the heat transfer rate at the tip, right? So Q at L is equal to 0. Okay. And the way we can formulate this is we can use Fourier's law, right? And so Fourier's law, remember, is K times the cross-sectional area AC times dt dx, okay? At x is equal to L is equal to 0, okay? Right. And so if we substitute theta into this, right? In other words, we substitute for this derivative here. Okay? We can also divide by KAC because we assume that they're constants. Okay. Then this tip condition becomes a lot simpler. So all we can basically say is that d theta dx at x is equal to L is equal to 0. Right. So mathematically, this is a lot easier, but we do have to make an assumption, right? And so we basically have to assume that the heat transfer from the tip is negligible. Okay? This is a reasonable assumption when our fin itself is very, very thin. Okay? Okay? In other words, AC is small. Okay? So I can draw a skinny fin here. Okay? And so let's assume that this is our fin, right? Oh, question.
Well, what do you mean by small? Is there like a minimum or maximum, like small?
Yeah. No, it's a great question. So small here is definitely relative, right? And so the thing that you're comparing here is the lateral surface area of the fin versus the tip area. So I don't have like an exact number for this because a lot of times it kind of depends on the application. But usually, if it's at least I would say if it's about 1% of the lateral surface area, I think that's pretty good. That's a pretty good threshold to be considered small. Yeah. And so we can say that AC here is about or less than or equal to 0.01 AS. Okay. Right. That's kind of a number that I honestly kind of made up that number here on the fly, but it kind of gives you an idea. Yeah. But of course, that exact number will depend on the application. Okay. And so if the tip surface area is only about 1% of that, you can basically assume that most of the heat transfer is going to come off the lateral surface. Right. So there's very little heat transfer that's going to go out the tip. And so in those situations where you have a thin fin, then you can assume that's adiabatic, and that simplifies your math quite a bit. Okay. Question.
So just the bigger the surface area of the tip, the more heat will be carried in flat.
Exactly. Yeah. So if you have a bigger tip area, then then you can't make this assumption and you might have to go with condition 1. Yeah. Okay. All right. All right, so that's number 2. Number 3. Number 3 is we're going to make an assumption that we know the temperature at the end of the fin. Okay. So in other words, we have theta of L is equal to theta L. Okay. Okay. So again, this mathematically, this is simpler, but I'd say this is probably the most difficult one to get because unless you have something that's measuring temperature at the end of your fin, where you know exactly what temperature it's going to be when you put it in this situation, then this is normally very hard to achieve. And so this is kind of more of a mathematical kind of convenient condition, but physically, practically speaking, this is normally very hard to achieve because it's hard to compute what the temperature at the end is. So that's what you're solving for, and so it's hard to know what you're solving for before you actually solve it. Okay. All right, and number 4, and so this is the one we're going to be using most often, is we're going to assume that the fin is very long. Okay. And of course, here very long is again kind of a subjective thing, but there's kind of a physical reason why we do this. Okay? And so by assuming that the fin is very long, then we're eventually going to reach a state such that the end of the tip or the tip of the fin is in thermal equilibrium with the fluid. Okay. Okay. And so in other words, in the limit when L goes to infinity, what we assume is that theta of L is equal to 0. Okay. Right? Because what does this tell us, right? Remember, excess temperature or theta here is excess temperature. And so if excess temperature is 0, what this means is that the temperature at the end of the fin is going to equal the fluid temperature. Okay. Right. And kind of the physical reasoning behind this condition kind of goes back to kind of the fundamental reason why heat transfer takes place in the first place. Because the reason heat travels from higher temperature places to low temperature places is so that they can achieve thermal equilibrium, right? And so everything wants to be brought to the same temperature. And so if you have a fin that's long enough such that it allows this to happen, then eventually the tip of your fin is going to reach the same temperature as the fluid. Okay. So if we draw a situation here, okay, so we have a long fin. Okay. Right. Eventually, when we reach this point right here, this is going to be the same temperature as the fluid. Okay. Okay. So does that make sense? Any questions of kind of the physical reasoning behind this this tip condition here? All right. And so the reason we use this one is that mathematically it's the easiest one to do. Okay, so let's come back to our general solution. Okay, so remember our general solution for the tip temperature distribution looks like the following. And so we have C1 E, and the exponent here we have a positive HP over KAC, okay, multiplied by X plus C2 E, the negative square root of HP over KAC, times X. Okay. All right. We have a very unique boundary condition here because we're making the assumption that as X goes to infinity, then we get a bounded solution. Okay. And so in other words, so because of tip condition, okay, our solution must be bounded as X approaches infinity. Okay. All right, so we have two terms here in our general solution, right? And so we have basically a positive exponential, so e to the positive number multiplied by x, and then we have another term which is e to the negative number multiplied by x. Right? One of these guys is going to behave really well when x goes to infinity. The other one is going to blow up, right? And so the one that's going to blow up is our C1 term, right? And so, if you draw the graph of an exponential like this, right? So let me draw it down here. Okay. You draw the graph of this guy. It's going to look something like this, right? So this is e to the positive number x, right? And so if x goes to infinity, then this is just also going to keep climbing and climbing up. Okay. You compare that to the graph of e to the minus x. Okay. Right? E to the minus x looks something like this. Okay. Right? And so as x goes to infinity for e to the minus x, then this is going to asymptote down to 0. Okay. And so what this tells us is that since x goes to infinity is part of our solution now, then this term is just not going to, it just can't exist, right? Because if that term exists, then as we take the limit as x goes to infinity, then that term is just going to blow up, okay? And so this term right here just cannot exist for this tip condition. And so that's great. So that eliminates one full term from us. And then so we're only just left with the other term, okay? And so if you remember our base condition, remember theta at 0 is equal to theta base, okay? And so if we plug this into our remaining solution, we have C2 e to the minus square root of HP over KAC multiplied by 0, okay? And so if we multiply by 0, then we get e to the 0, and e to the 0 is just 1, right? And so this tells us that C2 is equal to theta b. Right? And so if C2 is equal to theta b, then we get our final solution for our fin temperature distribution. Okay, so theta x is going to be theta b times e minus HP for KAC times x. And so that solution there is our temperature distribution in our fin. Okay. Temperature distribution for a really, really long fin. Okay. All right. Any questions on this? Yep.
So if the Fullerton reaches thermal equilibrium, does that mean no heat loss or heat transfer?
It is. Yep.
So that coincides with the
it does. Yep. Yep. So condition 4 right here also overlaps with condition 2. Except condition 4 is it's a little bit more strict because condition 2 we can achieve the same conditions as condition 2 without having a really long fin, as long as your tip is very, very tight. So four is a little bit more restrictive because we're requiring the fin to be really, really long, but it also accomplishes the same thing as condition 2. Good observation. Question? Okay. All right, and so let me plot this. And so let's go ahead and let's note some trends. Okay. Okay. And so if we have a plot, it looks like this. And so on the x-axis, we have x, and then on the y-axis, we have theta, okay? And so this plot here is going to start at theta b, right? And so that's going to be the high point of the graph. And then it's going to be an exponentially decaying function, okay? So it's going to look something like this. Okay. So let's make some observations on this graph, right? And so it looks just like a very simple, exponentially decaying graph, but there's some important physical things to note. Right? So this is always, I always love these parts of the class because we get a result like this, it looks kind of deceptively simple. We have just simple decaying exponential. But there's kind of physical reasons why we have it like this. And I think looking visually at a result like this and kind of giving physical explanations as to why we're getting this result, I think is part of the reason why analytical work like this is really cool. Okay, so let's make the first observation. So the first thing that we notice is that the temperature in the fin is just obviously decreasing down the length. Okay. Okay. So that's kind of like, stating the obvious, right? Sky is blue. But, there is a physical explanation for this, right? And so if we draw the fin, right? And remember, we're tracking the temperature as we move from the base toward the tip of the fin, right? And so what's happening as we go from the base to the tip, right? As we move from the base to the tip, the fin is just naturally losing heat due to convection, okay? And so because the fin is losing heat, then, of course, as the fin loses heat, then the temperature is going to decrease. Okay? And so the decrease in temperature that you observe is due to the fact that, we're constantly losing heat to the fluid as we go along the fin. Okay? Okay. Right. So again, simple result, but I think it has an interesting, intuitive kind of physical explanation. Okay. Okay. Another observation that I want to make is the fact that the temperature gradient is also decreasing with x. Okay. Okay. And so what do I mean by temperature gradient, right? And so what I mean by that is the slope of this line, right? And so if you look at the slope, just visually, just from the beginning of the line, okay, the slope of this line is something like this, okay. If we compare that slope to somewhere down the length, it's significantly more flat at the tip end of the fin, okay. Okay. And so why is this? Well, I mean, literally the reason is because that's just what an exponential looks like. But physically, this is because, as heat is lost to the fluid by conduction, this also decreases the conduction heat transfer through the fin. Okay. And so as you go along the fin, there's just less heat that's being transferred throughout it. Okay. Okay. And last point I want to make, it's kind of a build off of one. And so we can call this point 1A, or we can call it point 3. Okay. Right. And so since the excess temperature is decreasing down the length of the fin, okay. Since theta itself is decreasing down the length, this means that the convection heat transfer is also decreasing down the length of the fin. Okay. Because the convection heat transfer, what does convection heat transfer rely on? Convection heat transfer relies on the temperature difference between your solid object and the fluid, right? And so if that difference decreases down the length of the fin, that means the amount of convection heat transfer is going to be more efficient or higher at the base of the fin. Okay. All right, and so what's the upshot, right? And so what's because of all these 3 points together, what is that telling us? Okay. And so what this is telling us is that at the base of the fin, or near the base, okay, near the base of the fin, since the temperature differences or the temperatures are the highest there, that's where we're going to get the most heat transfer. Okay. And this temperature is going to decrease, as you get further and further, and that heat transfer is going to decrease as you get further and further along the fin. Okay. Right. And so from a design perspective, this tells you that, if you have the choice between making a long fin and a really, really long fin, right? What that's telling you is that kind of inch per inch, or like kind of foot for foot, for each more material that you add to the end of the fin, it's not going to give you as much bang for your buck, because most of the heat transfer is going to be occurring at the base of the fin. Okay. And so, sometimes you do have to add more length. And so, sometimes you do have to add more surface area just to achieve your thermal targets. But just know that, to make, a bigger difference, compared to the base of the fin, you have to add just that much more length to the end, just because the heat transfer is just a lot more inefficient at the tips. Okay. All right. Any questions on this before we do an exam? Okay. All right, so let's do an example that kind of puts everything together, because I think we've been talking theoretically, this whole time, and so I think it'll be helpful to do an example to kind of talk about the applications. Okay. All right, so in this example, let's assume that we have a very, very long rod. Okay, and so in other words, we're going to assume that we're under condition 4. And let's assume that it has a diameter of 5 millimeters. Okay. And let's assume the base temperature at this fin is 100 degrees C. Okay. And let's assume that this fin is being cooled by just ambient air, so room temperature air, and the air has a temperature of 25 degrees C. Okay. Okay. And let's assume that the air has a convection coefficient of 100 watts per meter squared K. Okay. All right, so visually it looks something like this. Okay, and so we have a cylindrical rod. Okay. So it's very, very long. Okay. It's being cooled by air. Okay. And so the air has a temperature of 25 degrees C. Okay. And the H is 100 watts per meter squared K. Okay. And the base is temperature 100 degrees C. Okay. And let's assume that the thermal conductivity of the rod is 180 watts per meter K. Okay. Of course, the diameter here is 5 millimeters. Okay. Okay. All right, so given this information, let's compute. Let's compute the temperature distribution in the rod. Okay. 2. 2 is going to be a test of our assumption. And so, even though the problem tells us that we have a very long rod, number 2, for part 2 of this problem, I want to compute how long does this rod have to be in order to be considered very, very long. Okay. Okay. And so we'll do kind of a test of our assumption on that. Okay. Any questions on this? All right. And so part 1 of the problem, it's just going to be a plug and chug type of equation. Okay? And so since we're assuming this rod is very long, we can use our temperature solution from condition 4. Okay. And so condition 4 being, the solution when we assume it's vertical. Okay? And so just to refresh your memory, that solution was theta x is equal to theta b multiplied by e to the minus hp over KAC multiplied by x. Okay. All right, and so we actually have everything here that we can plug in. Okay? And so first let's compute theta b. Remember, theta b is our excess temperature at the base. Okay. And so theta b here is going to be the temperature at the base, okay, TB minus T infinity, okay, both of which were given in this problem. And so TB is 100 degrees C, T infinity here is 25 degrees C, and so theta b therefore is 75 degrees C, okay? And so conceptually speaking, we basically are saying that our base, the base of our fin, is 75 degrees C hotter than the fluid that's cooling it. Okay? And so our fin is 75 degrees in excess of the fluid. Okay, and so next we're going to compute the coefficient here. Okay. Okay. Right, and so we have square root of HP divided by KAC, okay? So H was given to us in the problem, so H is 100 watts per meter squared Kelvin, okay? K was also given to us in the problem, so K is 180 watts per meter Kelvin, okay? The perimeter here, since we have a circular or cylindrical rod, our perimeter of the cross section is simply going to be pi times the diameter, right? So it's going to be pi times 5 millimeters, which we're going to convert to meters. And so it's going to be pi times 0.005 meters, okay? And then area, cross-sectional area, is going to be the cross-sectional area of a circle. And so we're going to have pi over 4 times the diameter squared, okay? So this is pi over 4 times 0.005 meters squared, okay? Okay. And so you can plug all that in, and what you get is you get 21.08, okay? And I believe this has units of 1 over meters, okay? Because it has to cancel out with x, okay? And so if we plug all that in, then we get our temperature distribution is equal to 75 times E to the minus 21.08 x, okay? And then of course you can plot that as well. As you, just so that you can visually see what the temperature is. Okay? So this is a pretty extreme temperature distribution. And so you can see the exponent value is minus 21. And so this temperature is going to decay down extremely quickly, okay? And so it's not really going to take that much time at all, okay? All right, any questions on how we obtain this result? Okay. All right. So one thing I forgot to cover is how can we compute the total amount of heat loss from the fin? Okay. So we can do that here as well. Okay. In other words, we want a quantification for how much heat is this fin offloading to the fluid. Okay. And so we have our fin that looks like this. Okay. And we want to compute, the total amount of heat that gets lost, right? And so the total amount of convection heat loss that comes off from the outsides, okay? Both from the lateral surface and from the tip. Okay. So from a design perspective, this is something that's really important, right? Because if you're going to be adding a fin to a device, you want to know how much heat is actually going to be offloaded from that fin. Okay. And so at first, this seems like it's challenging, right? Because we have we have an entire lateral surface that we're computing on. Okay. And just like we talked about earlier, since the temperature is decreasing along the length of the fin, right? Then the convection heat transfer along the length is going to be changing, okay? And so it's going to be really high at first, and then it's going to decay down as you go along the length. And for this case, since we're assuming the fin is very long, it's going to decay down to 0. Okay? And so how can we sum up all these convection heat losses if it's changing along the fin? Right. So normally in a case like this where where you have a quantity that's changing over a period of distance right here, one way that you can do this is you can integrate. You can basically sum up all the convection heat losses down the length of the thing, right? And so one way that you can do this, you can say that Q is equal to, we have theta here, and so we have an integral of theta of x times h times as of x, okay, dx. That would be the cranky engineering professor way to do this, but there's a more clever way that we can do this that involves a lot less pain and a lot less integration. Okay, and so this is one way, and if you're into math, that can be a fun thing for you to do, but we're not going to do it like that. Instead, we're going to make kind of a very clever observation, okay? And our observation is that, in order for the heat to leave the fin off the lateral surface, every heat that the fin loses, or every piece of heat that the fin loses, has to pass through a certain point, right? Okay. And where is that point? That point is the base, right? And so the fin itself, remember, we're assuming the fin itself is not generating any heat, right? And so that kind of defeats the purpose of having a fin to begin with. And so the fin is supposed to offload heat, right? And so you're not going to make it out of any material that's going to generate heat. You're not going to lace it with any heaters. Okay? And so all the heat that the fin experiences is going to come from the base, right? It's going to come from the device that's generating heat. Okay. And so one way that we can compute the total amount of heat loss from the fin is just to compute the amount of heat transfer that passes through the base. Okay. Okay, and if the heat passed through the base, then it's going to go out the outside of the fin. Okay, it's simple, conservation of energy. Okay, and so and so basically what we have is that Q of the fin is going to be equal to Q at the base. Okay, and Q at the base here is going to be, we're just going to use simple Fourier's law. And so Q at the base is going to be minus K times AC times d theta dx evaluated at x is equal to 0. Okay. And so I'm going to give you kind of the general formulation for this, just so that you can kind of plug in for stuff later. Okay. And so remember, if our theta of x is equal to theta b multiplied by e minus HP over KAC, okay, times x. If we take the derivative of this, we take d theta dx is equal to theta b, and the exponent is going to come out, and so we have a minus HP over KAC, okay, times e to the minus HP over KAC multiplied by x, okay? If we evaluate this at x is equal to 0, then this is going to turn into 1, right? Because we have e to the 0 power, which is just 1, okay? Right? And so if we plug this in, we get QF is equal to minus KAC times theta B times minus square root of HP over KAC, okay? We do a little bit of the math here. And so we have a KAC up top. We have a KAC on the bottom, okay? And so those are going to partially cancel out because one's under a square root, the other one's not, okay? We have a minus sign that's going to cancel out here, okay? And so for a case where you can assume that the fin is very long, then the total amount of heat transfer that, that leaves the fin is going to be equal to square root HP times KAC multiplied by theta B. Okay. And so this right here is the total heat loss from fin, from very long fin. Okay. All right. And so just to kind of put a bow tie on this example for now, I know we didn't do part 2 yet, but we'll do that on Wednesday. If we go ahead and plug the numbers in from this problem, then we get QF is equal to 5.6 watts. Okay. Yeah, I can scroll back up. All right, and so this fin right here, you know, this fin that's only 5 millimeters in diameter is only going to offload about 5.6 watts worth of heat. Okay. All right, any final questions on this before we wrap it up for today? Okay, all right, and so on Wednesday, we'll go ahead and finish up this example. There's just a little bit left. Then we're going to talk about fin performance. And then from there, we're going to talk about 2D heat conduction. And so that's going to be a really cool topic. Okay, so thanks everyone for tuning in today. Hope everyone enjoys the rest of the afternoon, and I will see you all on Wednesday. Hey, what's up? Yeah. No, right. So for fin, the conduction heat transfer is just the heat transfer down the length of the fin. Right. And so if you think of kind of what we just talked about, all the heat that's coming to the fin is coming in from the base, right? Okay. And so that heat, you know, some of that heat's going to get lost to convection, right? So that just immediately exits stage of that, right? But then some of that is going to travel down the length of the fin as well. And so that's why we like conduction heat transfer. So that's the heat that's actually traveling down the solid part of the fin. I mean, eventually all of it's going to be lost in the fluid, but you can almost think of it as like a 2 branching path. And so when the heat first comes into the base, you know, it can either be lost to convection right away, right? or it can just continue traveling down the length of it. So that'd be Q conduction.
That's why along the fin there's different temperatures.
Exactly.
Got it. Okay, that makes sense. Thank you.
Yep.